And I'll get those references put together for you. Which are you most in need of? Like kind of the high level education research, which Rachel has led, or
I think
summary
that I
curricula?
mean I would love to say some stuff about the efficacy stuff, but I think that probably the for the administration who I'm trying to convince to give me more money, I think student retention and interest in majors and stuff is really the thing that's going to make the most impact to the
Yeah.
folks I'm speaking to.
Yeah, I have some stuff where I discuss what happened at UNC. We That's part of our goals for the education research team to track retention and stuff. But it's been we didn't really know how to do it. Uh, we wanted to, the idea is by participating in Opus and MWU, STEM majors would go up. But that's a difficult thing to measure across all STEM disciplines. All sorts of different phenomena could be going on
Sure.
that can make things go up and down. But what we experienced at UNC with the introduction of Opus, and that's back when Clues and I were doing it here at UNC, is enrollments went up by like a factor of by 100% in all of our intro astro courses, and over the course of about 5 years, and then kind of leveled off. And it's fluctuated since due to all sorts of other effects, but and our majors went up 300% from 10 AstroTrack majors to 40, and we still retain the 40 number today. So
Awesome.
I can send some documents that describe that.
Yeah, that's great. Thank you.
Okay, cool. Well, welcome back, everyone. Let's see. Last time, well, before I start blathering, everyone should grab that data. I sent some data in the email, and I just say it's a big file. It's the Eagle Nebula file. And there's a copy of it in the workspace, but the infrared has already been integrated into that. I want to show you how to do that. So, in the sample directory, I mean, in the sample directory, we have this file, but it already has the infrared integrated, and I want us to work through that either this time or next. So I sent you the file with just the optical. So download that and upload it into Afterglow. And here I'll share just to show you all how to do that. And I'll blather for a few minutes while you're all doing it. Put you over here, spread you around. Okay. Afterglow. And so it's this file right here, the M16. I just opened it myself, actually, so it's going to take a second for everything to load. But you go to Open Files, and it's not going to let me do it until it loads these images here. Look at Okay, so you go to Open Files, you go to your workspace, and you upload, and you find the file that you downloaded and put it in there. And if it fails to upload, that means your workspace is full, in which case you want to go back and find something else here, uh, like this stuff Kent just sent me. I guess I'll show some of that. And you can then download it so you don't lose work that you've done and delete it and make space for the new file you're going to upload. Let's see. Yeah, this wasn't on my list of things, but last time, let's see, Dave was here. Yeah, I don't see him here right now, but he pointed out that last time we did the big radio project, which I'm really excited about, the module 4A, where the students divide up 15% of the sky into 16 maps. Each map is like 20 degrees by 20 degrees. So it's a huge chunk of the sky. And they all map their region and investigate it and then put it together into a mega map. And we talked about all that last time. And Dave pointed out at the bottom of one of the pieces, we have Vela. Is it Vela? It's what was it?
It's the Cygnus loop.
The Cygnus loop, and in there it has
The
what is it?
Veil,
The
Veil
veil.
Nebula.
Nebula.
Veil.
Yeah.
Thank you. So Eastern and Western Veil, if you're familiar with those, that's right here. And this project's just been fun because it's a bunch of blobs. I've seen these blobs for 30 years as we mapped them as part of my Arriver program. But now we have that cool tool that my student Reese made where you can click on the blobs and it takes you to Simbad. You can figure out what they are. And I hadn't looked at this one, and Dave realized it was the Veil, part of the Cygnus Loop, and he mapped it. Kent and his students went and mapped it, and you sent me one of the images. I went back and reconstructed it. Since you mapped it in galactic coordinates, I need to make it in galactic. The one you made was in equatorial, which is one of the cool features of this radio stuff. It's just
Hmm.
a stream of data, and we're making the image. So you can map it in one coordinate system and make it in another. Anyway, I went back and remade it and attached it with different background subtraction scales because it's kind of big. So you may want to use a larger background subtraction scale, else you may wipe out pieces. But yeah, it fits nicely. So now I'm doing a test of whether I can just make this map just a little bit bigger to include it and still stay within one file. If the maps get too big, they get split between files and Skynet kind of breaks. Anyway, let's see. Most of you probably have this uploaded by now. So let me check my notes here. Right, so just setting this up, this is module 3, going backwards now. Module 3 it's the longest module to do with the students. You kind of start it early on, and it kind of runs in the background for many weeks as they're collecting their data and processing their data and learning how to do new things with the astrophotography, and then adding infrared and doing calculations. So it's kind of a long running project, and we're just getting ready to finish it up now. And we'll probably spend 2, maybe even 3 sessions on it this semester, hopefully 2. And in terms of setup, module 1 is introductory stuff, optical and radio. Module 2 is kind of intermediate, particularly with the astrophotography. They learn how to do red, green, blue combinations calibrated to background stars. Here in module 3, you can call this advanced, though it does, of course, get even more advanced with like the very serious astrophotographers out there. But by advanced, I mean we're going to be including luminance layers and narrowband layers and infrared layers. And I see Matt's down here. Matt played a big role in developing this project and has written one of the papers on it. Anyway, there are kind of 2 parts to this. Doing the astrophotography part, which we'll focus on this time, and maybe a bit next time, depending on how long it takes. And then the calculational part that Matt really spearheaded. And I just love how this project comes together. The astrophotography is cool. And then you use everything in your image. You use the infrared, you use the narrowband H alpha, et cetera, to get temperatures in different regions. And we do a Stromgren sphere calculation, a pressure balance calculation, and just using stuff in your image, you can calculate densities and temperatures of your region. So calculational stuff next time. The way this module works. So here's module 3, the current draft version of it. I didn't get a chance to update this one. I'm trying to update them all as I go through, but I fall behind and I'm writing the new modules 4A and 5C, so I didn't give this one an update. But there's a table here. These are all big, bright, popular objects. Most of them have popular names. Some of them don't, so they have the NGC number there, but most of them have a popular name. And each team in the class picks one, though they have to pick one that's currently observable. Down here, there's a link to the optical observing guide. And one of the first things in that guide is a table. And so we start this one, we collect our data like in February. So they have to pick targets between 5 and 15, right ascension. And if we look at the table here, we have a whole bunch, kind of around the Orion constellation side of the Milky Way. And then there's a big gap, right? As that part, I guess I can bring it up in Skynet. Let's just do that. Add a new observation. Here's now. And so, here is, I think I'm on the radio side, but anyway, here you have this side of the galaxy. Orion is around here somewhere. I can't find it right now. Where is it? Anyway, and then, but you got to start this early, as early in the semester as you can, because if you wait until like now, then the sun's too close to it, and there's just not very much time to collect data before the sun comes up. And then you have that big gap, and then what that gap is basically this side of the sky right here. We don't see it because the sun is in the way. Yeah, not much there. And then I just turned off the sun essentially. And then you have this other side of the galaxy over here. So that pops back in. You have the other side that's good in like the fall semester. Anyway, lots of cool targets here. And then what do? They design their observation. And we're not going to do that. It's all described. And I see you all kind of jump really quick. So I know my internet's kind of crappy. Hopefully it's not too bad. You're getting most of it coming across. Okay. Clues is like so. Which internet am I on? Yeah, just coming back.
Yeah.
Okay. Well, hopefully it's not too bad. And so what I was saying is once they pick their target, they plan their observation. We're not going to spend time on that today. It's all written up. But one thing we introduce them to is using oculars and stellarium. You can build these little boxes here where you designed it for your telescope and for the camera on the telescope. And then we're doing M16. And so that, this region, what's great about Stellarium is all these regions, these big, bright, popular regions, they have little messy thumbnails in here, and their image will be better than this, so it's not a spoiler, but it can help them plan, particularly framing. Now, it's a little sad because the oculars are in red, and often the nebula are in red, but, you can position for whatever telescope camera combo you pick, and some have bigger fields of view, some have smaller fields of view. You can frame it up, and there are coordinates here that you can then read off and 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 design, and that's what you enter into Skynet. So they collect observations, not just red, green, blue, but also luminance and also narrowband. They do a test observation first just to make sure that they're using good exposure times, and they adjust their exposure times, and they look at the narrow bands and make sure that it's going to be worth it, because narrow bands are very expensive. They're very long exposures, typically 5 minutes each, and they don't want to waste their time if there's no narrowband emission. So there's a whole process of them designing their observation, doing a test, and then doing the main observation. And then for the main observation, they normally do 5 sets. They run through all the filters 5 times, and with like 30-minute gaps in between, just in case one screwed up by RBI from a bright object, it doesn't screw up all the sets. And that makes a fairly shallow image. It'll be a little bit noisy. The idea is, as we offer this year after year after year, we're building up a lot of archival data. So they'll start by collecting some of their own data, and then they can go into the Skynet archive. Let me pull up Skynet again here. And the archival search is really crude. It'll be better in Skynet 2. Optical side, you just go to collaboration observations, and that searches across all educational institutions. Why won't this take? Okay. And then something like Messier 16. And right now, as long as that name's that's part of the name or in the header, brings up all the M16 observations. And they're looking for kind of big ones, and then they go in there and they check them and make sure, oh, these are good exposures. They're long, they're framed similarly to my own, and I can use them. And we'll create better search capabilities in Skynet too. But they go into the archive and then grab whatever has been done previously and build that in to have a nice deep image. And that's what I've sent you. Okay. So I think we can get to it. Does everyone have this thing loaded up in Skynet now? Well, everyone except me because I hopped off it. There's my, let me see which layers. This might be why my internet's a little jumpy. It's trying to do this at the same time. Clicked on this a while ago. Hope it didn't like give up. No, it looks like it's filling things in. That's good. Almost there. Okay, I think everything's in now. So let me walk you through these layers. Each one of these is a stack. And this is a very deep stack. It's not just 5 deep. This is probably 20, 30 images deep. It's a popular target, right? So the R looks really good. Boy, I'm getting slow response time here. V looks really good. Oh, I'm on B. That looks good. And then here's my luminance layer. It's solid. Then my 3 narrowband layers. Here's H alpha. Looks fantastic. But the other two are a little bit weaker, and that's often the case. Often H alpha is very strong. O3 you can see is kind of noisy. And S2 is just really, really noisy. But I'll show you the tricks. There are tricks that we can actually incorporate this and hide the noise quite often. Okay, first thing we do is we're going to order these in a particular way and color them and set the blend modes. Okay, so make sure the color ones are at the bottom. BVR doesn't matter the order. And then the luminance, you can just grab it and slide. Put the luminance on top of the color layers. And then H alpha, O3, S2. So your RGB combo, like in module 2, we learned how to do an RGB. I always get paranoid about this. I know I hit the record button, but I'm just checking. I am, yeah. Okay, module 2, we learned how to do RGB. Now we're going to learn how to make an LRGB combo. It becomes a unit. And I'll describe what the luminance does in a second. Then H alpha above it, that's your best narrowband. Then O3 and S2, lesser and lesser narrowbands, typically. Okay, is everyone ordered? Okay, now we're going to color each and set their blend modes. So the red layer, I'm going to color this. Oh, my computer's lagging. It's painful to do a demo when you got the lags going. The red layer red, the green layer green, the blue layer blue. I'm actually going to remove this file. That file's huge, as is this one. That may be what's lagging my browser. I'm going to close Stellarium too. Don't need that. Hopefully that will help. Okay, luminance layer, we leave that gray. Now what the luminance layer does is we take the signal to noise from this layer and the color from whatever's underneath it. So we're going to calibrate the RGB with respect to the background stars and get the color correct for dust and all that kind of stuff. And that will provide the color, but the intensity will come from this layer. And usually the idea is the luminance, it's a broad filter, covers the red, the green, and the blue. And so you can get higher signal to noise in this layer and hence get a better quality image, taking signal to noise from here. And so what you do with luminance, you right click and you set the blend mode. Instead of screen, which is the default, you change the blend mode to luminosity. And that's what makes it a luminance layer. It now, as it's working its way down this list, it'll say, okay, I hit a luminance layer. It's going to take the intensities from here and then the colors from whatever's underneath. Okay. Now for the remaining ones, these are the narrow bands. I'm going to click on it here. For H alpha, we're going to start with natural colors. Okay. And so I've designed custom palette into custom colors. So H alpha, if I go to color, oh, color map and pick bomber. I'm still laggy. That didn't help anything. But bomber, this is the color of the bomber sequence. I think I have it here in the color combination guide. Yeah, you can see here the narrow band. So here's the red filter, the green filter, the blue filter. Here's H alpha in the middle of red, S2 on the red side of the red, and O3 kind of between the red and the blue. And we're not using H beta. It was just in the plot that I stole. And we're just looking at H alpha. That's the red of the four visible bomber lines. But whenever you have the red, you also have the other three, the blue green, the blue, and the violet. And for typical temperatures of star-forming regions, I calculated how intense they are relative to each other and figured out their combined color. And so it's called bomber and afterglow, and you can just set this layer to bomber if you're trying to get natural colors. In a little while, I'll explain how to do unnatural color palettes because they're fun. And the other thing you want to do is you change the blend mode here from screen to lighten. So blend modes are just their operations between this layer and the combination beneath it. What lighten does is it takes whatever is brighter, pixel by pixel, this layer or the LRGB combo below it. And the LRGB combo, that's stars. It's going to focus on stars. The narrowband, that focuses on the gas, the distributed hot ionized gas. And you can see stars in it because the stars also emit in that narrowband frequency. But by setting this to lighten, we can raise this layer so the gas wins, but in most places in the image, but not on the stars. The stars will still be dominated by the LRGB layer. And so you can have the gas, but you can have the stars with their natural colors that aren't being made pink by this layer. That makes sense. So for the stars, they'll come from the LRGB combo. They'll be the correct colors. And then for the gas, it will take it from this layer. Same thing for O3. We go to that layer. I'm going to color it. There's an O3 color. O3 is a doublet in the blue-green. I calculated both lines, and that's the combined color. And I'm going to set its blend mode to lighten. And then finally S2. Its natural color is red. And its blend mode will start by setting it to lighten. Okay. So everything should be set. I'll click on the top group and it will do a combination of all that. And it looks ugly at the moment, but you'll be shocked and amazed by how pretty we can make this look.
And just to be clear, the BVR images are just screen in terms of their mode.
Yep, that's right.
Okay. All right.
And screen is kind of like averaging the colors together. There's a fancy definition for it, but that's basically it. That's the default. Okay, we're going to start by making the LRGB combo. So to do this, we're going to turn off the narrowband layers so they don't distract us. So just click on the three eyeballs and that will turn them off. And here you see the preliminary LRGB combo. And we're going to work this one up very similar to how we did in Module 2 with the RGB combos. So the first thing we're going to do, you're clicked on the group layer. You come over here and we're going to select the luminance layer. It's the gray one. Here are the narrow bands. They're sitting on top, but right there's the luminance. Okay, I've selected that. And we are going to tie the RGB to it. And so when I change, once we're done, when we change the brightness and contrast to the luminance layer, it will automatically do it for the RGB as well. It'll be a single LRGB unit. And so under color composite tools, we're gonna link all layers. Oh my God. Link all layers pixel value. I should have done a reboot before this. My laptop's just really laggy. And well, that keeps me from getting too far ahead, right? And then after we link it pixel layer, we're going to go down to photometric calibration, like we've done before. And it usually will fill in the layers for you, but I've been screwing around too much and it's confused, so I got to pick them. Your red layer, your green layer, your blue layer. We're going to click this to measure the 0 points. And down here you see it's working on that. It's extracting the stars, comparing to catalogs, getting the 0 points, which are the relative amounts of each layer. The reference layer, we're going to set this to the red. It didn't matter before, but now we're going to set it to the red. There's a reason why. And let's start with extinction 0, as if there's no dust. There is a lot of dust along this line of sight, but we'll start with 0 dust. Let's see, is it done with it is done, so I should be able to calibrate this. And it will look very red. And it looks very red because there's a lot of dust there. But we'll correct this in just a second, just like we did in Module 2 by putting in an EBV. Everyone here, we've done this before. Okay. Now, for the dust, in Module 2, what we did is extracted all the stars, built HR diagrams, modeled isochrones, and measured the EBV, EB minus V. You can do that if you want, but usually you can go to this website here called WebDA. Now I'll just put this in the chat. And it's already set to this field. You can just change the NGC number to check out other ones. It doesn't always have an EB minus V, but right here under reddening, it often does. And with this one, it's 0.782. If it doesn't, oops, I want that. Yep. If it doesn't, I tell students to start with like 0.75 and treat it as a free parameter. And one of the things they can adjust until it looks good. Where was it? Okay, so I'm going to come back here down to photometric calibration. It's being more responsive now. That's good. Put in 0.782. Calibrate, and you're going to see this get bluer. So it has built-in dust extinction curves. And now the stars at the distance of this cluster are the correct intrinsic colors. Any foreground stars have been made too blue. Any background stars are still too red. I described this before as color focus. Like a camera, you can only focus it at one distance. With this dust correction, you can only get the color correct at one distance through a column of dust. But once you do that, you have the correct colors. And but there's one more thing we have to do, and it's not clear before we can make it pretty with the mid-tone level display settings. It's not clear on this one because the luminance histogram matches very nicely the red, green, blue. When we did
Dan,
that, yeah, please.
Can you just step back? Where did you put in that correction?
Yeah, it's right. I'm laggy again. Under photometric.
Back in the photometric calibration part, yeah.
Right down here.
Okay.
Yeah. So we tied everything to the luminance. And our luminance frame has about the same count levels as the red, green, blue. And so that's why this looks so good. It's not always the case. Maybe with luminance, we image twice as long. I mean, we have more counts. I'm just going to fake that right now. I'm going to put an offset here. I'm going to raise all the counts in the image by 100. So see how the luminance histogram shifted up to the right? And all the brightness and contrast controls are tied to the luminance histogram. We tied everything to luminance. And so here you see the background level and the saturation level. And all the color histograms are now below the luminance. So only the brightest things, this tail here, do you actually see the colors. So if there's discrepancy between the luminance layer and the RGB, right, the blue and the green have now been set to the red. This RGB is correct with respect to each other. But now we got to move that whole combo to be consistent with the luminance or move the luminance to be consistent with it. And there's a simple way of doing that. And if you go to neutralize sources, we're going to select the luminance layer and we're going to shift it down to the red layer. It's a shift and a stretch. So luminance to red, neutralize the sources, and we'll take that histogram and shift it down, which means it's going to subtract counts off every pixel in the image, and maybe you do a factor as well. And it just happened that before they matched up nicely, but now they match up as well as they're going to. So you can think of this as maximizing your color dynamic range. If they are mismatched, you're not using the full color range. Now they're well matched and you're going to have great color range. It's kind of a subtle concept, but
Hey, Dan, can I ask you a question? I don't
please.
want to get us too far afield. Is that okay if I ask?
Yeah, please.
So I'm just looking at my image and your image, and I've got some little features in those brightest stars down at the bottom center of the image. They
Yeah.
just look like they're Oh, you've got them too. Okay,
I do
never
too.
mind. All
You
right.
can see them on the Zoom. And so in this, the students take a test observation and then they scale their exposure so they don't saturate any stars. Because if you saturate, you can bleed. And
Right.
that's what happened here. And
Yeah,
and then when I aligned, the alignment algorithm doesn't, it interpolates pixels, but that bleed is so abrupt it has a hard time.
I see.
And
Okay.
these
Yeah,
pictures,
I was more concerned that you didn't look like yours was there and we were using the same images, so I didn't know if there was a issue on my end, but
no,
all good.
it's there.
Yep.
These images were acquired during an Aurora many years ago, and we didn't scale exposure times. So basically, at the very end of this, once you export it, you upload it into some editing software and just dab out those pixels manually. Okay. And now let's make it pretty. So we're on the luminance layer. And so we're going to change the stretch mode to midtone and then hit the default preset. Again, midtone lets you have your cake and eat it too. You see all the structure at the faint end, but you don't blow out all the stars at the bright end. We can tune it by tuning the midtone level, but we'll just leave that at 97.5 right now. Okay, so that's pretty cool. And often you may want to export and check. Sometimes in Afterglow, you may not, particularly if zooming out, it doesn't do a good job of deep working with the remaining pixels. If you have a really large image, it will look kind of messy, but you can export it into some photo viewer, and this is looking pretty awesome. That's just the LRGB. That's now a single solid unit. So now we're going to learn how to factor in narrow bands. Everyone here? Okay. So let's turn on the first narrowband, H alpha. And the image did get a little bit pinker, but let's do this right. So we've turned it on. We're going to come over here and we're going to choose the H alpha layer. This is now bringing up the display settings for the H alpha layer. And we can't really, a lot of them are hidden because it's linked to the luminance layer. So if you come down here and unlink it. So now we can control this layer independently of the LRGB combo. So we unlinked, and I think we then hit the default preset to get it back to standard values. Yeah, it did get a little pinker when I did that. And then it's all about setting the the background and the midtone level. So the background level, the way you set these, and we should have actually done it with the luminance too. It turns out I wouldn't have changed it. I'm not going to change the background on this one, but I'll show you how to set the background. You click on the individual layer and you look at its histogram. This is number of pixels of this pixel value. So the bright stuff's to the right, the stuff to the left is the background. It's logarithmic here, so we have a lot of faint pixels. And here you see the background level, and you want it to be just a little bit below where it peaks right there. And so, I'd leave this at 1. But in some of our lesser levels, we'll end up increasing this. And the luminance was the same. We didn't check it, but I'll just go here and you see the background is right below where it starts to peak. So I'll leave it at 1%. That means the lowest 1% of pixels are being turned black, but everything above gets a shade. Okay, I'll go back to the combo. Again, I'm on the H alpha layer. So now it's all about setting the midtone level. Remember, this is the light and blend mode. Whatever's brighter wins, the H alpha layer or the LRGB combo. Now, what I normally do is I start by setting this to I'm afraid because my computer's so laggy, 99.999, which essentially turns it off. If you raise the midtone level, the image gets fainter. So I always start by that, and then I ease it in. I take out a 9. Nothing popped up. And take out another 9. Nothing popped up. Take out another 9. I saw a little bit. It was real subtle. Let's go down to 90. Yeah. Do you see how it came in? So at this point, I've lowered it enough that the gas layer is winning over the LRGB in most places, but not on the stars. So the stars keep their color. Just to really demonstrate this, I'll go down to 50. So the H alpha layer is winning like almost everywhere, but it's still not winning on the stars because of that light and blend mode. Let me switch the blend mode to screen, the default, and you'll see the stars just got pink. They have their colors underneath, but now they're being averaged in with the pink H alpha. But if I put it back on lighten, then it's whichever is brighter. Where the gas is brighter, it wins. Where the stars are brighter, they win. And so you get to keep your natural stellar colors. Now I don't want 50, and this is really a matter of taste. This is the A in STEAM. I'm just sticking it back to 90 because I've played with it, but some people may prefer a little bit more, so maybe 80, a little bit less, maybe 95. Now, whatever makes you happy. Okay. Great. That layer was easy because it was so high signal to noise. Let's try the O3 layer next. I'm going to turn it on. And we immediately got kind of this ugly green. It's noisy. You see the noise all through our pretty image. Here, I zoomed in. I'll turn it off for a second. Oh, it's real pretty. Turn it on. And okay. So what are we going to do about this? Well, you start out the same way. We're going to come over here and switch to the O3 controls right up here and unlink it from the luminance layer down here, put it on manual. And then we get our controls. Let's put it on the default settings, which is 1 and 97.5. Okay. And now we're going to set the background. Like, look here in the dark region. It's just nasty green everywhere. And the human eye is really sensitive to green. And so if your green layer is noisy, oh my God, it can really ruin an image. So first, we're going to set the background. Again, you go straight to the O3 layer for that and look at the histogram. The background level is well below the peak. So let's try, instead of 1%, try 10%. See, it moved up and made now 10% of the pixels dark. Let's try 20%, 30. 30 is kind of at the peak. 40, yeah, 40 is beyond the peak, 30 is at the peak. So I'll go back down to 20. I'll be just a little bit below the peak, 20, 25, maybe 25. Okay. Now, if I come back up here, we'll see there. That helped a lot. In the dark areas, it got a lot better. It's still noisy in there. If you zoom in, you got green speckles. But the next thing you do is you play with the midtone level. kind of up the mid-tone level until the green layer is faint enough that you don't see the speckles. And sometimes it works, and sometimes you end up turning the whole damn thing off. So let's try 99. That will dim it. Helps, but I still see the speckles, maybe 99.1, sorry, 99.9. Okay, so that looks great. I don't see the speckles anymore, but I don't see any of the O3 at all. I basically made it so faint it's gone. If I switch it back on, no difference. So the only way we could get rid of the noise was to turn the layer off. But there's a trick. I can help you with this. So I'm going to put it back to 97.5. So we see it again. There it is. What you can do if you have a noisy layer is you can take it and slide it under the loom. So now I have my RGB, then I have the O3, then the loom. And remember, loom, it's a luminance layer because it takes all of its signal to noise from the loom and the color from underneath. So I just went from having intensity noise to something less egregious called color noise. Here, I'll zoom in here and I'll show you the transition. I'll put it up above H alpha again, and we'll see noise. And I put it below the loom. And now the intensity is coming purely from the luminance layer. I still have some noise, but it's color noise. Variations in the color. It's not nearly as egregious. If I turn the layer off, see, not a big change here in the dark regions. So I'm just going to leave that at 97.5. And it's really nice if you can use more than one gas layer. If you have one gas layer, it's one color and kind of blah. Having two, now I can mix colors. Now, personally, I just hate green in astrophotography. Again, the green, the human brain latches onto it. And so often, instead of using a natural palette, I use what I call the Skynet palette. I use natural colors for all the layers except O3. And I just make this a little bit bluer. We have a green-blue, where is it? Blue-green. Here it is, blue-green. O3 is a little greener, blue-green's a little bluer. And see, that's, what a relief. That's much easier to take on the eyes than that a little bit too much green. It's not what it would look like in reality, but and the intensities of the different layers are not what they would look like in reality. We're playing with the intensities. I just played with the color a little bit, and at the end here, I'll show you how to play with the color a lot. And it's okay because these are just indicators, right? It's a language that we're developing. This color means this color means that. We want the stellar colors to be realistic. So we do that careful calibration with LRGB. But with the gas layers, we get to have a little bit of fun. Okay. Everyone with me there? Okay. Now, what are we going to do with this god-awful S2 layer? Often S2 is so bad you just don't even image it. There's just nothing to work with. But this is just, it's noise everywhere. There's some detail that the dust there, where the gas is being heated, right, outlining. It has some great outlining features. It'd be nice to use it. Okay, so back to the main layer. I'm going to turn it on. Oops, I clicked on it. I meant to turn it on. And immediately will be like, yuck. Oh, I guess I have to decouple it. So let's go over here to the S2 layer. Same as before, bring up the S2 controls, unlink it, hit the default to get to our starting point. And it's here. You just see that red everywhere. In case you didn't notice, I'll just blink it. Off. On. Okay. So can we salvage this layer and do something with it? Let's find out. First, we're going to set the background. So again, we're going to click on the S2, raise the background until we're just a little bit below the peak. So 10, 20, 30, 40, 50 is at the peak, so I'm going to go back down to 40. That helped a lot. You could see how the image changed. The dark regions have gotten darker. So I'll go back to the whole thing and update there. That helps a lot. But still, we got a lot of noise. And so, you could play the same game. You could up the midtone level, and basically the only way you get rid of the noise is by essentially turning it off. So let's just immediately put it down here below the loom. That helps a little bit, but we still have color noise and a lot of it. And you can see I'll blanket, even though it's getting the intensity from the loom, just the colors are being, oops, I clicked on the layer. Turn it back on. The colors below the loom are being so disrupted by that noise that we have color noise. It's better than intensity noise. And again, we can play the game trying to get rid of it, but you're going to have to up the midtone level until it's essentially gone. So last resort, final trick that you can do is move it from lighten to screen. And because now you, instead of taking whatever's brighter, you're averaging it in, and you up the midtone level to something pretty faint. I've played with it and I find that 99.5 is pretty good. That dims it down. If I were in the lighten blend mode, it would be the same as turning it off. I just put in lighten and it's essentially off. I can blink it, nothing. So, there's nothing there. But by putting it in the screen, it's not a matter of taking whatever's brighter, it or the stuff underneath it. It's going to take it and the stuff underneath it. It will contaminate stellar colors a little bit, but we've pushed it down far enough that it's no longer dominating the noise, but it's still contributing. Like if we come over here to the talon or the beak or whatever, and I blink it, you'll notice a difference. Off and on. See how I kind of outlined it? And so now we're incorporating a third layer, a different color, and it just gives it a little bit more definition. So we were able to use it even though it was incredibly noisy, but we had to put it below the luminance and we had to turn it on to screen and tamp it way down and use just the brightest parts of it. So that is an LRGB plus narrowband combo. And you can export it. Export. Yeah, okay. There's a pop up here a couple times. Open it. Yeah, it's looking pretty cool. Here, I'll just give it a rotation and flip to get in the right orientation. So here we have stars and we have gas. We don't have infrared yet. That'll be next time. But in the final 11 minutes, I think what I'll do is show you non-traditional color palettes, because very few people actually use natural colors. Or this, which instead of a natural palette, this is what I call the Skynet palette, because remember I took the O3 and made it just slightly bluer so it wouldn't be so ugly. But that's pretty. We got stars, a lot of bright O stars, but red stars too. We have the gas, it's all highlighted. The gas is telling us temperature information. The luminance layer is giving us this nice structure in here. We come back here and zoom in and I turn off the luminance layer. It got a little worse. And also, I can no longer use it to hide the other layers, but okay. Unless there are any burning questions, I'm going to quickly show you color palette options, narrowband color palette options. Okay. Now to do this, I'm not going to try to make the image pretty. In fact, what I'm going to do is I'm going to put the O3 back up above the hydrogen. I'm going to put the S2 above the O3. S2 above the O3, please. It sometimes, there we go. And I'm going to set their midtone levels all to 90, just so they're all highly visible. So the idea is once you get a good color palette that you like, then you play the noise games again that we just learned. But here I have all three with, that's the Skynet color palette. Let me go to the O3 layer and put that back on O3 so you have a natural color palette. Okay, there's a natural color palette. Just don't worry about the noise. The point of this is just to show you the colors. Now in module 5 here, module 5 we do star death. Module 3 is star forming regions. Module 5 it's pretty much the same deal. They pick targets, star death regions like planetary nebulae, supernova remnants. And there aren't as many calculational physical lessons here, so we leaned into the STEAM. And here's where we show them the non-traditional or the non-natural color palettes and encourage them to, make something interesting looking. So we separated it out and put this into module 5A. But here's natural. Here's Skynet, where I changed O3 to blue-green. Here's the Hubble palette. What Hubble does is it takes them in order. I think I still have that over here. The reddest one, they make red. The next reddest one, which is in the middle of the red, they make green. And I'm sorry, the next bluest one. And then the next bluest one, which is blue-green, they make blue. So they color them red, green, blue in wavelength order, even though those are not their natural colors. And that's called the SHO, red for S, green for H, blue for O, or the Hubble palette. And then there's also HSO, where you switch the sulfur and the hydrogen because they're so close in wavelength. And there's also an HOO if you don't have an S2. And I can demo those really quick. So for the Hubble palette, S2 is red, H alpha is green, and O3 is blue. And this should automatically start feeling more like Hubble colors, right? Normally the star forming regions, the central regions are blue. That's due to the hottest gas, the O3 gas. Again, you'd have to play all the games with hiding the noise, but you can see the different color palette. That's SHO. Let's do an HSO. So in the HSO, the S is second, so it's green. And the hydrogen is first. We'll make that red. So this is an HSO palette. Again, our green layer is the S2. It's super noisy. And green, the human brain, and noise are a bad combo. So you're going to have to work really hard to hide that noise. But that's an HSO palette. And sometimes you don't even have S2 to work with. So I'm just going to turn that off. And people use the HOO palette. So hydrogen, they make that red. And oxygen, they make it both blue and green. So I'm going to pick the oxygen layer and change its color to blue-green. That throws it into both the blue and the green channels. And so that's your HOO palette. Again, you have to hide the noise a little bit. And lastly, let me put it back on natural for a second. So let's see. What are we on? We're on the O3. I'll stick that back on O3. Hydrogen, I'll put on bomber. And I'll turn on sulfur. And sulfur, I'll put on red. So that's back to natural. So this is something we did in-house. Sometimes it works, sometimes not. But on the color wheel, opposite the bomber color and the O3 color, what color is opposite? The idea is if colors are opposite each other on the wheel, like red, green, blue, they go together well. And so it's not exactly an equilateral triangle, but it's kind of close. And the thing that's opposite is a bluish color, and we call it harmony because it's supposed to harmonize with the bomber and the oi color. And so if I come down here, there's harmony. I colored the S2 harmony, even though it's a red one, I colored it blue. I think that's god awful, but you can also rotate them around. You can do a harmonized. What we just looked at right there is harmonized HOS, but you could do harmonized SHO, harmonized SHO, HSO. Anyway, yeah. So it's instead of red, green, blue, you have bomber, oi, and harmony, and you can put them through the same paces. And find a color palette that makes you happy, and then work on hiding the noise. Keeping in mind that the green one is, you probably don't want to make your noisiest layer the green one. Okay. So that is kind of, now you're all at the advanced level of astrophotography, and at least as advanced as it gets in MWU. Of course, in astrophotography software, there are all sorts of other things you can do. But again, we're trying to make it student level, where you achieve 85% of what the pro packages do for 15% the learning curve. And I think Afterglow does that nicely. Next time, I'm going to show you how to get the infrared data from Spitzer, ideally. Weiss, if Spitzer didn't hit that target or the data's no good, Weiss is a full sky survey. There's going to be some other full sky survey that will eventually replace it with better data. And also 2MASS in the near infrared is good for finding dust-hidden stars. So this gas that we're seeing in this image, that's star-heated gas. What we'll get from Spitzer and Weiss in the mid-infrared is star-heated dust, and what we'll get in the near-infrared is dust-hidden stars. So we'll get these other physically, no, it's not just making the thing pretty, although it will be pretty. We'll get these other layers that have deep physical meaning, build them in as well, and then spend some time calculating stuff and trying to tell a story about what's going on in the region. I'll shut up and the questions, comments. If not, I'll see you later.
Just a comment that, no matter how many times I've done this or gone through it, I just appreciate the opportunity to go through it again and learn something new every time. So thanks again. This has been great.
Yeah, this time it felt at pace. It felt like it was delivered at a pace that you could actually keep up with, which is not always something I'm good at, particularly with this. Matt knows because we've done conferences together where we have half an hour, and I'm trying to do the astrophotography in 15 minutes so he can do the calculation in 15 minutes, and it doesn't work well. But
Dan, I have a off-subject question.
sure.
Um, I if I have photographs that I've taken and I want to process with Afterglow, is there an easy way if I upload my flats and bias to like do the calibration in Afterglow, or do I have to do that beforehand?
No, you should be able to do an afterglow. In fact, I just asked Vladimir to send me a flat and a particular filter. We have a new telescope, and for whatever reason, it's just not getting a flat in the S2, and I have a
Okay.
lot of data. So there are pixel operations right here. Now, I haven't done what you're saying, but I think it should be easy. We go to the pixel ops, and so imagine loading in your flat,
Yeah.
or you can even make your flat, bring them all in here, and you have simple operations where you can take an image, you could take other images. No, no, this is image mode. What are the modes? Yeah, scalar is where you're doing like mathematical operations on an image. Image mode is where you're adding and subtracting and dividing and multiplying images together. So let's say I wanted to take the red layer, and let's say I also want to take the green layer, and I want to divide by, it can be the green layer, it could be a whole bunch of layers, if you need to do a bunch of
Right.
imaging. And I want to divide by the blue layer.
Sure.
I can overwrite the files if I want it. Oops, I clicked the wrong thing. Divide by the blue layer. They all have to be the same size, I think. And I'm not going to overwrite the files, and I'll submit it. Let's see what we get. It just created 2 files. The first would be the first operation, red divided by green. And here is red divide. Sorry, that was red divided by blue. Here's green divided by blue. And you
Yeah.
can then play with the ranges here so you can see things better.
Sure. No, this makes sense. This is great. Thanks. I know that's really off subject, but it's a thing.
Oh no, that's fine. And we have advanced operations where you can do fancier things too, if you know certain commands. And we'll use some of this next time. When we grab the infrared data, some of it will have holes in it because something was so bright it just saturated, and we have to fill the holes. And so there are little advanced commands. There's a whole programming language that you can use if you know it. Yeah.
Cool.
Anything else?
That whole programming language, the if you know it, is anybody actually documenting that?
Well, we didn't invent it, so it's some type of common image scripting language. Vladimir would know. I don't know where it
Okay.
comes from, but he would know.
So it's probably an external library that you
Yeah.
guys bootstrapped in here. Okay. All right. Cool.
That said, we should still point people to the proper documentation. I normally Vladimir's the document. I'm like, Vladimir, I need to do this, and he says, "Oh, the command." Blah, 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 blah. And
Well, this as always presupposes the not hit by a bus
Yeah.
level of documentation that we've always had at Skynet, which is that guy knows it. Don't let him get hit by a bus.
Now, I should say with Skynet 2, they're developing it like really, it's a new level of professionalism. And there's all sorts of great auto documentation, and we're using it. So when Skynet 2 comes out, it's going to be exquisitely documented. And it's already, as they code it, the AIs and whatnot, the algorithms, it documents it as they go. It's really awesome.
So speaking of AI, I have some conference follow-up, but we can do it next time. It doesn't.
Yeah, I forgot. I'm so sorry.
Yeah, no. All good.
You want to lead off with that next time?
Sure.
Okay, let's lead off with that next time, and then we'll do the infrared, and we probably won't get through all the calculational stuff, so this will probably be a 3-week training unit. All right. I will see you all next week.
Thanks. Bye.
Thanks, Dan. Dan, got just 1 second.
Yeah. Here, I'll
Hey, it's
stop.
Chris Rowe.
Yeah.
Just had a quick question about the